So, from our last lesson, we learned that fields were these zones around objects that could let them influence the motion of other objects with that same sort of zone around them. So, that's what a field is, right? And we know that objects with the same sort of fields can have this sort of influence on each other. So, any object with mass will generate a gravitational field around it, for example. And that'll let it attract with any other object that has mass and generates a gravitational field. And we also know that in the context of electromagnetic fields, for example, we can have positively charged objects attract negatively charged objects. And that is because of fields. It's what lets these objects attract each other without actually touching each other. But an interesting property of fields that I don't think many people cover is how the strength of fields changes as you get further and further away from the object that's generating the field. So, for a more concrete example, if you imagined we had a proton and we took these little steps away from the proton. Now, forgive my drawing here, but imagine this was an equal length, and you took these steps over and over again, and you went 1 unit away, and then 2 units away, and 3 units away, and so on and so forth, away from this proton. The question here is, how would this proton's field strength change, or how would this proton's ability to affect another charged particle change? Well, we can actually draw a graph for this. So if we map strength as a function of distance, and we looked at how does the strength of this field change, we'd actually see that not only for electromagnetic fields, but for things like gravitational fields, we have this sort of exponential decay pattern going on. And that's actually really counterintuitive, because you'd imagine something like a field to lose its strength in a linear fashion, but it doesn't. It decays exponentially. Now, the main reason fields behave like this is because they operate in a three-dimensional environment, just like all the objects in real life. Now, it's going to be hard for me to describe how this works on a two-dimensional blackboard, but let's just assume we have this analogy where we have a three-dimensional, perfectly spherical, perfectly constant source of light. And this light source emits beams of light that travel in perfectly straight lines. And let's also assume that we created this cage-like structure around our source of light. And this is also perfectly spherical, like a shell. And we'd imagine that this shell didn't let any of the light get out of it, and it measured every single photon of light as it hit the outer edge. Now, if you're wondering why we chose a spherical shell for this and not like a cube shell or like a right-based conical pyramid or things like that, the reason is because coming out of this light source, a beam of light is going to have to travel the same distance to get to the sphere no matter where we go. And that's important because we want to measure just how strong or intense the light is at a certain distance away from the light source. Okay, so now let's set up the final question. What would happen if instead of having a spherical cage set up at a distance of r from our light source, what if we increase that distance? What would happen then? Sorry, let me do this in a white color. What would happen if we increase the distance from our light source and made a bigger cage? Hopefully this ends up being a perfect circle or something close. If we did this, what would happen? Well, the first insight to think about is the actual amount of light being emitted doesn't change, it stays constant. But what does change is the area that's detecting that same amount of light. So when you have the same amount of light and a greater area that light is quote unquote spread over, then you're going to have less photons hitting every unit area of our detector. So for educational purposes, let's say 10, right? And the reason, of course, again, is this light is spreading out, right? The distance between these arrows is growing, right? These arrows are diverging, and less light is hitting any one point on this larger detector. So are you ready? Here's where everything comes together. So we know that this cage is spherical, and we're judging things in terms of surface area here. And if you know geometry to, let's say, grade 10 or 11 level, we know that the surface area of a detector like this would be 4 pi r squared. But can you see where this behavior is coming from? It's the squared on this r. And in fact, as we have these linear increases in r, so as we go from 10 to 20 to 30, and as we keep increasing r by a certain amount of units and taking these little steps, like I said, from our proton or whatever, as we take these little steps, the surface area increases exponentially. Once again, nothing changes to the energy. The energy is conserved. You can't create or destroy energy. But what you can do is make that energy dissipate out into a larger area, for example. And that's what we see. This detector's area is growing. And so let's say we had R is equal to 10. That would give us 400 pi as a surface area. But let's say we went from r is equal to 10 to r is equal to just 20, and we had this increase in 10, right? And so that's also the same as saying the light has to travel 10 more units to get to our detector. Well, what would happen there is we have 20 squared, or 400, and 400 times 4 pi gives us 1600 pi. So for this 2 times sort of increase in the radius, we have a 4x growth in our surface area. And this is going to continue. If we went from 10 to 20, 20 to 30, and so on, we'd have this exponential increase in surface area, right? And that leads to an exponential decrease, this exponential decrease in field strength, right? Because field strength as a function of unit area depends exactly on the surface area itself. Once again, the strength of the field depends on the surface area. The energy is not changing, the surface area is growing. And so that same amount of energy gets split up into smaller and smaller pieces. By the way, this is called the inverse square law for anyone that's curious. And this is the mechanism, right? In 3D space, this is how things behave.